Good afternoon. I'm Peter Ye from Ieit. I'm also one of OCP China community leader. And unfortunately, Cassie Wang, my colleague, the intended presenter of these slides, is unable to attend, so I will be sharing on her behalf. If you have a further interest, please feel free to contact me after the meeting. I can introduce more and recommend her to you. It is well known that applications like AI and big data have led to the increasing prevalence of high capacity hard drives. However, when hard drives exceed 30 terabytes, we will face big challenges. So today's topic is discuss the challenge and the solutions. I'll firstly to recall the HDD dynamic surrogate, which OCP storage group have working on since 2021. Then come Iet's application of OCP surrogate, analysis of HDD dynamic risk, and acoustical solutions. At last, I will show you the sound absorption efficiency of tubular acoustic silencer developed by Ieit. Previous white paper of the HDD dynamic workstream in the OCP storage group have highlighted that high frequency noise can introduce resonance in micro-scale components of HDD. When the cumulative displacement of the read-write head surpasses a critical threshold, it is lead to a significant degradation in HDD IOPS. The purpose of OCP HDD dynamic surrogate is to develop tools to standardize the measurement and the communication of HDD dynamic disturbances and risk across ID industry companies and ensuring data consistency. All the spectral data presented is acquired with OCP acoustics and vibration combined HDD dynamic surrogate. With the OCP acoustic and vibration combined HDD dynamics surrogate, we can get SPL, which is a sound pressure level, spectrums in the server enclosure. We can discover how SPL varies with transmission paths, even when measured on the top and the bottom surfaces of one HDD. And the insertion of foam or honeycomb mesh leads to a significant decrease in SPL across 5K to 10K Hz. Acoustical solutions make acoustical insertion loss, which can be detected by the surrogate as well. Through the insertion loss curve, we found the sound dampening capability of porous foam ranges in a broad spectrum and dominates in high frequency range of 7K to 9K Hz. When we change the thickness, material, or areas of the foam sheet, the IL peak amplitude changes as well, but the dominant frequencies don't change. In this slide, I'd like to share the susceptibility frequency identification method that Ieit utilized in development, which help us with the analysis of HDD dynamic risk. The susceptibility measurement system is able to sweep the HDD unit with noise across a 9th octave bandwidth to detect its susceptibility frequencies and threshold. The picture on right bottom presents the raw result from the sweep test. It is a 2D matrix showing the performance degradation of each step. Here I provide a real report for one HDD. The first row is the SPL step for sweep test, and the first column is the center frequency of 1/9 octave bands. Combining the PSD spectrum with the HDDs threshold of acoustical excitement, one can get the figure on the right. In the figure, we can see some frequency components exceeding the HDDs threshold contribute significantly to the most substantial reduction in HDD IOPS. And some further analysis has proved that there is a direct correlation between excessive frequency exposure and performance degradation. If one can selectively dampen these critical frequencies, the disturbance to HDD will be effectively mitigated. With that in mind, I'd like to introduce the acoustical silencer theory. The acoustical silencers are typically engineered according to the Helmholtz resonance cavity theory. The principle involves the creation of resonance within the cavities, which interacts with the acoustical waves, effectively diminishing the energy of the outgoing wave. The resonance frequency, denoted as Fp, is a critical feature to be designed. It is influenced by 3 key factors: the areas of the neck, the thickness of the neck, and the volume enclosed within the cavity. When the frequency of the incoming wave matches Fp, the silencer achieves a significant transmission loss, enhancing its noise reduction capability. Each cavity within the silencer can be tailored to address a specific frequency, allowing for a targeted approach to noise mitigation. Please refer to the diagram on the lower right, which illustrates a recommended design for an acoustical silencer. The design features a tubular structure that ensures airflow can pass through unimpeded, while the acoustical waves are attenuated by the resonant cavities. Moving forward, we'll focus on the technical aspects of the tubular acoustical silencer, which presents a significant challenge in mechanical design. The objective is to integrate this silencer within the limited space of compact server and JBOD enclosures without compromising on thermal performance or sustaining accessibility. To achieve this, the acoustical resonator is strategically positioned in the gap between the fan wall and the HDD. The placement is crucial as it allows for sufficient clearance for the silencer's design, while also ensuring that the airflow remains unobstructed and the HDD remain easily accessible for maintenance. Once installed within the server, the tubular acoustical silencer take on a form reminiscent of an air duct, which is a significant improvement over the appearance of traditional silencers. This design choice not only enhances the visual appeal, but also ensures that the silencer blends seamlessly into the server's architecture. However, when you take it off and look inside, you can see several tubes, each aligned with one L move axially in each tube. There are one or multiple L cavities, each tuned to resonate at specific frequencies. This design allows for targeted noise reduction across a range of frequencies, improving the system overall acoustical management. Let's proceed with an analysis of the tubular acoustical silencers performance. Begin with the finite element analysis. Simulation results presented in the figure at the lower left. The horizontal axis indicates frequency, while the vertical axis represents transmission loss. It's important to note that a higher transmission loss signifies a more effective silencer within the system. The graph displays 3 distinct resonance peaks, with the additional peaks that are considered side effects of the primary resonances. To further validate our design, we fabricated several 3D printed prototypes and integrated them into server enclosures. Utilizing the OCP dynamic surrogate, we quantified the insertion loss of these silencers. As depicted in the figure at the lower right, the black line corresponds to the silencer, the green line to the foam, and the red line to the honeycomb mesh. Our silencer demonstrated a 6 dB improvement in acoustical performance over traditional solutions, a significant enhancement in noise reduction capabilities. In the context of HDD operation on the specific workloads, increasing the fan speed from 60% duty to 100% duty can adversely affect HDD IOPS performance, potentially causing it to fall below the cooperation specification threshold. This scenario indicates that the HDD may be at risk under such utilization patterns. In some worst-case configurations, neither porous foam nor honeycomb mesh prove sufficient to mitigate this risk. However, through systematical validation, we have determined that an acoustical silencer, which cavities tailored to the susceptible frequency of the HDD, can markedly enhance HDD IOPS performance. This improvement allows the HDD to meet the cooperation specification, maintaining IOPS performance at over 85% of the maximum limit. Continuing from our previous discussion on the performance implications of high fan speeds on HDD, we observe that when HDD are subjected to structural vibration from air movers, traditional solutions like rubber pads or rivets were once sufficient to mitigate performance degradation issues. However, with each new generation of HDD, the capabilities of this drive increase. In the same time, with the IT devices advancement, Elmore rotates faster to cool the dense and more powerful components within the enclosure. This results in stronger acoustical waves, which in turn worsen the performance degradation issues of HDD. In such cases, the problem can only be addressed with more sophisticated acoustical solutions. The conflict between the need for high-performance fans and the susceptibility of HDD to acoustical vibration has intensified. Current solutions, including porous foam and honeycomb mesh, are proving to be insufficient in the most extreme configurations, potentially impacting product compatibility and performance. The silencer cavity are designed to target the frequencies to which the HDD are most susceptible, significantly improving HDD IOPS performance to meet or exceed cooperation specifications. By doing so, the silencer ensures a stable and reliable operation of HDD, even in high-density server environments. In conclusion, the integration of an acoustical silencer is a strategic advancement in managing the acoustical challenges posed by high-performance fans and the increasing capability of HDD. This solution not only addressed the immediate issue of performance degradation, but also future-proofs our systems against the growing demands of high-density server environment. I'd like to call to these actions. First, utilize OCP HDD surrogate to measure the dynamic of server JBOD enclosures. Second, analyze and discuss the HDD susceptibility with HDD designers. At last, try to define the insertion loss target and design acoustical silencers. If you are looking for technical cooperation, please contact Cassie Wang, who is the conductor of this speech and is able to feedback to any question regarding with this slide. And Ivan Xu, who provides partnership in the silencer development. At last, let's make a summary through this speech. OCP acoustical and vibration combined HDD dynamic surrogate provides benchmark of acoustical analysis and comparison of solutions. Due to HDD natural property, server JBOD enclosures need frequency targeted solutions. The integration of such a silencer is a critical step in ensuring the reliability and efficiency of HDD in high-demand environments. It demonstrates the importance of acoustical engineer in the optimization of HDD performance, aligning with the objective of the OCP storage group HDD dynamic management initiative. So at last, I'd like welcome if you have more interesting related the OCP China Day, because I'm the OCP community leader. You can contact with me, and if you have interesting on this topic, can contact with the Cassie Wang and Ivan Xu. Thank you.